I will do the assembly of the emulator to show you what well, at least what has been my preference in terms of the in terms of the assembly process for the emulator. So, like all the electronic devices that I always build, I try to do it by the height of the components. So let's start with the resistors and the diode that is on the schematic. So I'll start populating the resistors. So what I have here is some broken nails. 2 of the 330 ohm resistors. So I just in my hands bend them to the correct shape. Sorry, this nail really bothers me. And I'll just populate them straight away in the board. So the 1.6 version of the board has got the resistor values, or pretty much most of the stuff values written on the silkscreen. So that's the 330 resistor. As you can see, I kind of put it the upside down. The resistors, they kind of fit snugly, so they will probably not fall out. So that should be fine. So that's one of the 330 resistors. And by the way, 330, you know the markings on the resistors based on the colors. So there's 3, 3, and 1 for the multiplier. So it's 330 ohm. So that's our 2 330 ohm resistors in the board. What else we have? We need some 10K resistors. Let's put 2 of them on the board. And we want at least one of the 4.7. Okay. 2 of the 10 ohm. And we also need one of our diodes. So I now have most of the resistors that I need. So for resistor R3 and resistor R7, I'm still using 10Ks. I have plenty of those 10Ks resistors, and this resistor here is not really that crucial. It's a pull-up resistor, so for R3 you can stick to 10K, and that's what I'm going to be supplying in the kits that I sell. So 10K for R3 and 10K for R7, just like that, and 10 ohm for R6, so 10 ohm, again 1, 0, so 1 brown, 0 black, and 0 for multiplier, another black, so 10 ohm for R6, 10 ohm for R5, and lastly R4. Where is R4 hiding? R4 is 4.7K. Okay. This is all in the schematic for the version 1.6. And then the Schottky diode, you got the black band for the orientation. So those components are all similar height. and they are the lowest height on the PCB. So all those can be soldered together in one smooth move. I'm going to flip it upside down. Obviously I'm going to be soldering under the camera, so it's not going to be the pinnacle of my soldering skills. I'm using this wire soldering tip. It's not really meant for through hole, but I like it, so you'll see I'm using this one. So like all the best practices for soldering, you touch the pad, let it heat up, and feed a bit of solder, just like that. Try to do those. Oops. Okay. So that's our resistors nicely soldered. So by the way, I used to use those Xantronic cutters. Unfortunately, they are a little bit worn out. One fantastic feature of those Xantronics was this extra metal bit here. What it does, I mean, it's not effective anymore. It's become loose, so that's why I stopped using those. But what normally used to happen when it worked is when you make the cut, this extra bit is supposed to hold the lead, so the lead doesn't go flying. With those large or long leads, not a big deal, but sometimes you have smaller leads. When you snip it, it flies across your room, and you don't know where it lands. So best practice, if you're cutting, hold the leads. You don't want them to land somewhere randomly, or worst case scenario in your power supply or appliance, or somewhere where it's important. So we'll cut all those together. Okay, so that's our resistors done. So in terms of height, I think those were the first ones. The second thing to solder is most likely going to be those precision sockets for the resistor networks, and that was a recent change to the BOM. I introduced sockets, or precision sockets, for those resistor networks. Because I want you to be able to swap those if needed. And what I mean by that, I'll show you later, but generally speaking, some platforms don't like the 10K pull-up resistors that we have in the design. Namely, the ZX Spectrum is very picky, and the 10Ks on the OE, the output enable line, that was a no-no. It just wouldn't boot with that resistor. So you could isolate the resistor network, but I thought best thing to do, because every target is different, and I thought maybe best thing to do is to give users option to choose whatever you want to have in that resistor network. So that's what I do now. I provide this precision socket. By the way, I've only soldered one pin. I'm a bit OCD, so I want those sockets to be nice and square. So after straightening and making sure that I'm happy with the alignment of the resistor network, I can solder the rest of the pins. Okay, so we have the resistor networks and resistors and diodes for now. The rest is the biggest exercise, which is the actual sockets. Watch the orientation, so the dimple or the small cutout has to match. So we've got the cutout here, and I'm matching it with the cutout on the, or the symbol on the board. So now what you want to do is you want to flip it upside down. I'm using the actual 3D printed tray to flip it upside down, and it can stay on top of the tray. That's fine. That is absolutely fine. Now, if you're worried about soldering, do just one pin, or one pin on each side of each IC, and then flip and double check if you've got everything right. I've done this many times now, so, but I'll still show you the process. So I'm just doing one pin on each side of every IC. So once I have all of them tucked, all of them, you know, just soldered one pin, I'm just double checking, is everything fine? Is the orientation of all the sockets correct? Yeah, okay. Now that I'm happy, now comes the bulk soldering. So once again, instructionally, best practice, touch the pad and preferably angle the soldering iron the way that you're heating up the pin and the pad at the same time. You give it a couple of, you know, half a second, and you feed the solder. Okay, so that's all of our sockets soldered on our beautiful emulator. What are we gonna do next? Diodes. I should have done the diodes, probably the LEDs, probably before the sockets, but that's fine. They'll sit nicely this way anyway. So diodes. I always remember that inside the diode we have the small bit and the large bit. As you can see, small bit, when the diode is brand new, not a problem. You know, the longer lead goes to plus, the shorter lead goes to minus. But if you're reusing LEDs, you don't know, because, you know, they will be cut already. So this way, if you can recognize inside, if you can see inside the LED, there's the big structure there and the small one. Okay, so the small one is plus, it's the longer lead. So on the emulator board, plus for the green one is for indicating of power, and there's a small plus sign on the 1.6 version of the PCB to tell you, to help you orient the LEDs correctly. So plus the longer lead of the LED goes to the plus on the PCB. Okay, so I've got those. Similarly to what I've done with the IC sockets, I typically solder one of the leads first for both. And then I flip to the other side, straighten them if needed. And if I'm happy with the way they look on the PCB, I'm a bit OCD, so I want to make sure that I'm happy with those. I'll just solder them. Okay, so that's the LEDs. Important steps, or important step. LEDs have quite interesting construction of the legs. It's much stronger than typical resistors, so I will just trim them a little bit so that we don't have any of the residue of soldering, like that and like that. And we'll take two of the longer ones, or two of the longest ones, maybe those two. The other one can go to the recycle. Then I'm gonna take a pair of pliers, or a pair of tools that will help me shape those things. Sorry, I'm doing it under the camera, so I'm kind of winging it, so shape it like sort of this way. Where's the camera? So kind of roughly this way. Those are meant to go to those connection points here on the PCB. So one goes to here for the ground. What are they for? In my production of the emulators, I use those connection point. I use those to connect test tools, multimeter, when I verify if everything is working. I've got a small jig that I plug in to verify functionality. So that jig needs power and ground as well. So I add those so that I can easily plug in. It's also useful, you know, when you're trying to power your logic probe. You're doing some testing, you're writing your new firmware, and you are troubleshooting a device, or maybe your firmware or whatever, and you are using a logic analyzer, or not logic analyzer, but let's just say you're using a logic probe. There's nothing like having a nice, easy space to plug the power for your logic analyzer, plus and minus for your logic analyzer. Just gonna snip. Okay, so we've got those. So this is for power, DCC, and this is for ground. Okay, what next? Let's install the push button. And this is for loading the code, or loading the content out of the SPI EPROM into the SRAM. So that's the switch. 1, 2, 3, 4 legs. Okay. So we've got the LEDs, we've got the push button. I think the next one, I mean, it's not really that crucial what goes first, what goes second, but right now I think the best thing to solder on would be the decoupling capacitors. So 100 nanofarads for most of them. 100 nanofarads, it should write 104, or you should be able to read on the capacitor itself. 104, that's 10, and the multiplier, that's 100 nanofarads. So we've got 1, 2. So the ones that are 100 nanofarads, I didn't put the value. They are just your standard decoupling capacitors. So I'll just put 3. 4 and 5. Okay, like I did with the sockets, I'm just gonna now flip it with the use of that 3D printed base, and we have 1, 2, 3, 4. Notice I'm putting my fingers on top of the wire that I'm cutting so that it doesn't go flying into my power supply, landing on an important trace inside power supply or between components that are important, and burning the whole power supply. I'm talking to you from experience, a not very pleasant experience of breaking something really badly because of exactly that situation. Right, so we have a small 22 nanofarad capacitor as well. (22 nanofarads), so we expect 2, 2, and 3 for the multiplier. So that's our 22 nanofarads. I'm just going to hold it with my hand and flip just like that. That's done. Transistors. So there are 2 transistors in the design, NPN and a PNP. So let's get them installed. NPN goes to Q1, which is 4401. And PNP, which is 4403, goes to Q2. Currently I've got those not shaped TO92 transistors for Q2, but actually I prefer them in a way because they don't fall out. You can just stretch the legs a bit and kind of wiggle them in. Okay, so that's in. Q1, which is the 4401. Of course, follow the shape on the PCB, so it has to be oriented. They have to be facing each other, those two transistors. Oh, what else is missing? The sockets for the Arduino. Or the... Yes. So they sort of want to sit parallel to the PCB without too much wiggling. The best way to achieve it is to put them in and sort of hold the PCB firmly against the desk whilst you solder at least two connections on each side. So I'll do one here and one here, so that's two of the pins, and I'm quite firmly holding it against the desk, so this way that connector is supposed to align itself to the surface of the PCB. 1, 2. Okay, but you also want to sort of verify if we're on the right track, and as you can see, they are both sort of okay. I'm happy with them. Okay, and if I'm happy, that means I can solder the rest of the connections. Okay, so that's the Arduino sockets. We've got one capacitor still to be soldered, fuse, capacitor, and the big connector for the probe. Let's do the connector. Now watch out, because the connector is kind of tight fit with the PCB. So don't bend, don't angle this, don't push too much stress in one side of the PCB. If it's not straight, that connector has got, will have problems getting in. So kind of so now that we have this plug-in, let's just solder it. Okay, so we have the sockets, we have almost everything. The last two items that we need to solder is the 10 microfarad capacitor. Let's get one of those. And the polyfuse. Where is my polyfuse? Polyfuse here. Okay, let's do the capacitor first. Remember, band on the capacitor is minus, so facing the minus there, plus is on this side. That's a small capacitor, 10 micro, 10 volts. Actually, the last item that I solder is that fuse. Okay. In theory, that's all we need to do in terms of soldering the PCB itself. We can temporarily install it in our base plate. Our base plate needs rubber feet. So base plates. Obviously I will later clean up this board because we don't want to leave it like that. I mean, it's just flux, but it looks ugly, so we'll clean it up. The board will fit kind of snugly into the 3D printed base, so that's done. The only last bit of soldering that we'll do before we turn off the soldering iron is the Arduino Nano. So I pre-programmed them, so they'll come programmed already. You don't need to do anything. For the kits, obviously, that I'm selling, on purpose, I'm not soldering the programming header for the in-system programming on the Arduino because it sticks out. I don't like it. It looks ugly. To help me solder, I just put the pins into the socket of the programmer before I populate it with all the chips, and align the Arduino Nano into those pins. Okay, watch out that you don't align into the wrong holes. There's enough hole. There's like a extra, I don't know what is this, mounting hole or tiny hole here, so there's a chance you could shift the whole thing by one position and solder everything wrong, so watch out for that. Anyway, this is now in. We'll solder it now. A voltage regulator, yeah. But the clones are a couple of bucks versus the $20 for the original. So I don't know, how do you justify? I mean, fair game for some of the newer Arduinos, but the Arduino Nano is a product that has been on the market for so long. I think they've made enough money on it. They should offer it now cheaper. Charging 20 bucks for it is, I think it's just way too much. Okay, I think that's all I want to do for this episode, or for this video. In the next video, we'll just populate or clean the board, populate the elements, and get it going. I'll also cover in the next video how you build the actual cable, the cable that goes into this connector. Okay, thank you.